The cosmos holds secrets that defy even our most brilliant scientific minds. You are about to journey through 25 of the most baffling astronomical phenomena ever recorded, cosmic puzzles that remain stubbornly unsolved. By the end, you will know the edges of our understanding and the mysteries that lie just beyond. We will confront a signal from the void so shocking it was literally circled and labeled WOW, and a force so dominant it makes up most of the universe yet is completely invisible to us. What single cosmic mystery makes you question everything you thought you knew out in the vast, silent ocean of space? A single, powerful wave once crashed upon our shores. It was the evening of August 15, 1977, at the Big Ear radio telescope in Ohio. Volunteer Jerry Amon was routinely reviewing computer printouts of the sky survey when his eyes locked onto a column of alphanumeric code. The sequence was so extraordinary, so statistically impossible for a natural origin, that he circled it in red pen and wrote one word beside it in all capital letters. Wow, for 72 glorious seconds, a narrowband radio signal, perfectly aligned with the hydrogen line frequency that scientists had theorized aliens might use, blazed from the direction of the constellation Sagittarius. It was 30 times louder than the background cosmic noise, and then, just as suddenly as it arrived, it vanished. Decades of frantic searching with more sensitive equipment have followed, but the signal has never, ever repeated. Was it a message, a cosmic hello that we simply failed to answer in time? Or was it the fleeting signature of some colossal, unknown natural event, a stellar burp or a quirk of interstellar plasma that we have yet to understand? The WOW signal remains a ghost in the machine, a one-night stand with the cosmos that continues to haunt our search for answers. That ghostly signal from the void is not the only cosmic whisper we cannot decipher. Far more pervasive and perhaps even more fundamental is the mystery of the universe's missing mass. Look up at the night sky, at the pinwheels of distant galaxies, and you are seeing a cosmic lie. What our telescopes reveal is only a fraction of reality. The rest, the overwhelming majority of the cosmos, is made of something we cannot see, touch, or directly detect. We call this phantom presence dark matter. Its story begins not with light but with motion. In the 1930s, astronomer Fritz Zwicky was studying the Coma Cluster, a vast collection of galaxies. He calculated how much gravity should be holding the cluster together based on the visible stars and gas. The answer was shocking. There was simply not enough visible matter to keep the galaxies from flying apart. He proposed the existence of Dunkel Materie, dark matter, to account for the missing gravitational glue. Decades later, Vera Rubin provided even more compelling evidence by studying how individual galaxies spin. According to the laws of gravity, stars on the outer edges of a spinning galaxy should move much more slowly than those near the center, just as Pluto orbits the Sun far more slowly than Mercury. But Rubin's meticulous observations revealed something astonishing. The stars at the edge of a galaxy orbit just as fast as those near the core. The only possible explanation is that each galaxy is embedded within an enormous, invisible sphere of matter, a halo whose gravity whips the outer stars around at breakneck speeds. This galaxy rotation curve problem is one of the most direct proofs that our universe is filled with something we cannot see. We can even map the shape of this invisible stuff through a cosmic trick of light called gravitational lensing. The immense gravity of dark matter warps the fabric of space-time itself, bending the light from galaxies behind it like a giant lens, distorting their shapes into faint cosmic smears. By studying these distortions, astronomers can trace the outline of the dark matter scaffolding that holds the entire cosmic web together. So what is it? The leading idea is that it is a new, undiscovered type of elementary particle. One candidate is a WIMP, a weakly interacting massive particle, a heavy particle that barely interacts with normal matter except through gravity. Another is the action, a theoretical particle that is fantastically light but could exist in such staggering numbers that it adds up to the mass we are missing. Yet despite decades of searching with incredibly sensitive detectors buried deep underground and powerful particle colliders, we have caught nothing. Dark matter makes up about 27% of everything in the universe. It dictates the structure of galaxies and the fate of the cosmos, and we have absolutely no idea what it is. If dark matter was the universe's missing skeleton, then its unexpected motion reveals an even deeper secret. For most of human history, we believed the cosmic expansion following the Big Bang was gradually slowing down, pulled by the relentless grip of gravity. That all changed in the late 1990s when two independent teams of astronomers made a discovery so shocking it won them the Nobel Prize. They were observing distant stellar explosions called Type 1, a supernova. These supernovae act as perfect cosmic lighthouses, their known brightness allowing us to calculate their distance with incredible precision. By measuring how much the light from these explosions was stretched or redshifted, they could also determine how much the universe had expanded since the star blew up. The data revealed something impossible. The most distant supernovae were significantly dimmer than they should have been, meaning they were much farther away. The expansion of the universe was not slowing down at all. It was speeding up. Some mysterious, repulsive force was stretching the very fabric of space itself, fighting against gravity and pushing galaxies apart at an ever-increasing rate. This force was dubbed dark energy. Imagine blowing up a balloon with tiny dots on its surface, then watching in astonishment as it begins to inflate all on its own, faster and faster, the dots racing away from each other. That is the reality of our cosmos. Dark energy is now measured to constitute about 68% of the entire universe, the dominant component of everything. But what is it? The leading and simplest explanation is that it is an inherent property of empty space itself. Even in a perfect vacuum, quantum physics suggests that virtual particles flicker in and out of existence, granting the void a constant, low-level energy density. This concept, called the cosmological constant, was first proposed by Einstein and later abandoned as his greatest blunder. It may now be his greatest posthumous triumph. The problem is that when physicists calculate how strong this vacuum energy should be based on theory, the number is wrong. Not just a little wrong, but 120 orders of magnitude wrong. It is the worst theoretical prediction in the entire history of science. This colossal failure tells us our fundamental understanding of physics is incomplete. Other theories suggest dark energy is not a constant but a dynamic force field, an evolving entity that has changed over the life of the cosmos. Some even more exotic ideas propose that our theory of gravity itself, Einstein's general relativity, breaks down on the largest cosmic scales. We are left with a universe where the fate of everything is dictated by a phantom force we cannot explain. A force that seems determined to tear the cosmos apart in a final, cold and lonely end. While dark energy works on the grandest of scales, a single, unassuming star 1,500 light-years away presents a puzzle just as profound. Designated KIC 8462852, but better known as Tabby's star, it was just one of many being monitored by NASA Kepler telescope. Kepler's mission was to find planets by watching for the tiny, periodic dips in starlight that occur when a world transits or passes in front of its sun. Most stars show these predictable, repeating patterns. Tabby's star did not. Instead, it displayed a pattern of dimming unlike anything ever seen. The star's light would drop by staggering amounts, sometimes as much as 22%, and it would do so in chaotic, asymmetrical, and utterly unpredictable ways. These were not the clean, repeating dips of an orbiting planet. This was something far stranger. The data revealed one monstrous dip where the star's light output fell by a huge margin for days, and then a series of smaller, jagged dips that looked nothing like any known celestial event. The immediate and most seductive explanation was the stuff of science fiction. Could this be evidence of an alien megastructure? Astronomer Jason Wright famously suggested that a Dyson swarm, a vast collection of energy-capturing satellites built by an advanced civilization, could explain the irregular, massive blocks of light. It was a hypothesis that captured the public imagination, turning an obscure star into a global sensation. Of course, scientists sought more natural explanations. The first was a massive swarm of comets, thousands of them, breaking up and creating vast clouds of dust and debris that would intermittently block the star's light. Others proposed that the star had recently consumed a planet, creating a cloud of shattered debris, or that it was surrounded by a warped, clumpy disk of protoplanetary material. But each of these ideas faced serious challenges. A comet swarm large enough to cause such dimming seemed statistically improbable, and data from the Spitzer Space Telescope revealed that the material blocking the light was not emitting the infrared warmth you would expect from a circumstellar dust disk. The star itself is also behaving oddly, showing a long-term, century-long dimming trend that makes the mystery even deeper. Years of intense observation have followed, with astronomers and citizen scientists alike watching Tabby's star relentlessly. We now have more data, but not a definitive answer. The latest studies point toward fine, circumstellar dust as the most likely culprit, perhaps distributed in a highly irregular ring that causes the bizarre dimming patterns. Yet the precise configuration of that dust and what could have put it there remains unknown. The alien megastructure hypothesis has largely retreated, but it forced us to look more carefully. Tabby's star stands as a powerful reminder that the universe is capable of producing phenomena we have not yet dreamed of, and that sometimes the most compelling mysteries are found not in the darkness between the stars, but in the flickering of a single, peculiar sun. The erratic flickering of a single star is one kind of mystery, but the cosmos also unleashes bursts of power so brief and violent they defy belief. Lasting only a few thousandths of a second, fast radio bursts are the universe's most explosive and enigmatic flashes. The first one was discovered purely by accident in 2007, buried in old data from the Parkes Radio Telescope in Australia. Astronomer Duncan Lorimer and his student were reviewing archival recordings of the Magellanic Clouds when they found it, a single, colossal spike of radio energy that had occurred years earlier. It was so intense and so brief that for a time many doubted its cosmic origin, wondering if it was just a glitch from a malfunctioning microwave oven on the observatory grounds. This first detection, now known as the Lorimer burst, opened a new field of astronomy. These bursts are not just powerful, they are mind-bogglingly energetic. A single fast radio burst over its millisecond duration can release more energy than our sun puts out over 80 years, and they come from incredibly far away, from other galaxies billions of light-years distant. For years, every new detection was a one-off event, a cosmic flash in the pan that left astronomers scrambling. The mystery only deepened with the discovery of a repeater. In 2016, astronomers found a source that was erupting again and again, sending out multiple bursts from the same patch of sky. This proved definitively that whatever was causing these blasts was not a cataclysmic, one-time event like a star blowing itself to pieces. The source was something that could survive its own ferocious outbursts. So what cosmic engine can produce such a staggering amount of energy in such an impossibly short time? The list of suspects is as exotic as the phenomenon itself. The leading candidate is a magnetar, a type of neutron star with a magnetic field so powerful it could strip the information from a credit card from halfway across the solar system. Theorists suggest that starquakes on the surface of a magnetar, or sudden rearrangements of its insane magnetic field, could generate these brilliant radio flares. Other possibilities include the violent merger of two neutron stars or matter falling onto a black hole. There is even a more speculative and far more thrilling idea. Could these focused, incredibly bright flashes be power beams from interstellar light sails, engineered by an advanced civilization to propel their ships across the galaxy? While most astronomers consider natural explanations far more likely, the sheer power and brevity of these signals force us to consider every possibility. Each new detection, each repeating source adds another piece to the puzzle, but the complete picture of what creates these cosmic gunshots remains one of the most urgent and exciting mysteries in modern astrophysics. Deep in the silent expanse beyond Neptune, two robotic ambassadors were slowing down for a reason no one could understand. The Pioneer 10 and 11 spacecraft, having completed their grand tours of the outer planets, were on their way to interstellar space. Yet as scientists tracked their trajectories with exquisite precision, a tiny, persistent anomaly emerged. Both probes were experiencing a minuscule, constant deceleration back towards the Sun, a pull of gravity that was just a fraction stronger than our models predicted. This was the Pioneer anomaly, a ghostly tug that baffled physicists for decades. The deviation was almost impossibly small, about 10 billion times weaker than the gravitational pull you feel standing on Earth. But in the precise world of orbital mechanics, where calculations must account for every known force, this was a glaring discrepancy. Was it evidence of new physics? Perhaps a flaw in our understanding of gravity itself, or could it be dark matter exerting a slight drag from the halo of our solar system? For years, the anomaly was a favorite topic for theorists, a potential crack in the foundation of Einstein's general relativity. The solution, as it turned out, was far more mundane, yet brilliant in its detective work. A team of researchers embarked on a monumental effort to reconstruct the entire thermal environment of the aging spacecraft. They realized that the Pioneers were powered by radioactive generators which produced heat, and that this heat was dissipated through the spacecraft's bodies and electronics. Most critically, this thermal radiation was not perfectly symmetrical. More heat was being emitted from the back of the spacecraft's main dish antenna than from the front. This created a tiny but constant photon thrust, a recoil effect much like a very weak rocket engine pushing backwards. This gentle, steady push from the craft's own warmth was exactly the right magnitude to account for the observed deceleration. The case was largely considered closed, a triumph of meticulous engineering analysis over exotic physics. Yet, a whisper of mystery remains. When all the known thermal effects are tallied, the numbers come incredibly close, but perhaps not perfectly, to explaining the entire anomaly. Some researchers argue that a minuscule fraction of the deceleration could still be unaccounted for, a lingering hint that there might be something more to discover in the deep, dark quiet where the Sun is just another bright star. The story of the Pioneer anomaly teaches us a profound lesson, that sometimes the most alluring cosmic mysteries are solved not by looking out at the universe, but by scrutinizing the intricate details of the machines we send to explore it. The unsettling quiet of the cosmos, broken only by brief, unreadable bursts, leads to a question so profound it has haunted scientists for generations. Given the sheer number of stars and planets, the universe should be teeming with life, a galactic chorus of civilizations. So why do we hear only silence? This is the Fermi paradox, the glaring contradiction between the high probability of alien existence and our total lack of any proof. Physicist Enrico Fermi famously captured this dilemma over a casual lunch in 1950, bluntly asking, "Where is everybody?" The numbers are overwhelmingly on the side of life. There are more planets in the observable universe than there are grains of sand on every beach on Earth. With so many worlds and the basic ingredients for life seemingly common, it seems statistically inevitable that intelligence would have arisen elsewhere, and likely millions of years before us. A civilization with just a 1,000-year head start would possess technology so far beyond our own it would be indistinguishable from magic. They could have colonized the galaxy by now, spreading from star to star. Their presence, their engineering, their signals should be unmistakable. And yet, our telescopes see no alien megastructures, our radios hear no deliberate greetings, and our sky remains stubbornly empty. The silence is deafening, so what is the great filter that holds everyone back? One terrifying solution is the great filter hypothesis. This idea suggests that there exists some nearly insurmountable barrier, a critical step in the evolution of life that is so difficult to pass that it effectively sterilizes the galaxy. The frightening part is we do not know if this filter is behind us or still ahead. If it is behind us, it means something like the transition from single-celled to complex life is astronomically rare, and we are the lone survivors in a cosmic graveyard. If the filter is ahead of us, it means most civilizations reach our level of technology only to be wiped out by their own creation, perhaps by nuclear war, runaway artificial intelligence, or an unforeseen ecological collapse. Our continued existence would then be a ticking clock, not a triumph. Other solutions are less apocalyptic but equally mind-bending. The zoo hypothesis proposes that advanced civilizations are out there and they are fully aware of us. They have chosen to place our world in a kind of cosmic quarantine, a protected stellar park where they observe us from a distance, allowing humanity to develop naturally without interference. We are the exhibit in a galactic museum, and the rules forbid making contact, or perhaps the problem is one of scale and time. The universe is vast and ancient, and the overlapping lifetimes of technological civilizations might be vanishingly brief. Think of it like two Mayan empires trying to communicate by sending smoke signals across the Atlantic Ocean. The signals are sent, but the civilizations rise and fall without ever knowing the other existed. We could be living in a galactic dark age, our calls into the void simply unanswered because no one is currently listening. There is also the haunting possibility that the paradox has the simplest answer of all. What if the filter is not a single event but the very nature of life itself? What if the emergence of complex, intelligent tool using life is not a predictable outcome of evolution, but a fantastically rare fluke, a 1 in a trillion cosmic accident? In that scenario, the silence is not a mystery to be solved, but the default state of the universe. We are not waiting for a message. We are alone in an empty cathedral, speaking to ourselves and hearing only the echo of our own voice. The Fermi paradox provides no easy answers, only profound questions about our own place in the grand scheme of things. Are we the universe's first children, its last hope, or simply its only lonely ones? That profound cosmic silence is echoed by a faint, ancient glow that fills every corner of the universe. This is the cosmic microwave background, the leftover heat from the Big Bang, a baby picture of the cosmos when it was just 380,000 years old. For decades, this radiation has been our most powerful evidence for the Big Bang theory, and it appears almost perfectly uniform, a testament to the cosmological principle. This foundational idea states that the universe is homogeneous and isotropic, meaning it should look roughly the same in every direction, with no special place and no preferred axis. But when scientists created the most detailed map ever of this primordial light, they found something that should not be there. They called it the axis of evil. This is not a name born of drama, but of genuine scientific perplexity. The subtle fluctuations in the CMB's temperature, the tiny hot and cold spots that seeded all future structure, are not completely random. Astonishingly, they appear to be aligned, however faintly, with the plane of our own solar system. It is as if the universe's oldest fossil somehow knows which way Earth is tilted. This correlation defies all logic. According to our most cherished cosmological models, the universe has no center and no edge. The solar system is an insignificant speck, and its orientation should be utterly irrelevant to the large-scale structure of the cosmos. The CMB should not care about us, yet the data suggests a link, a whisper of a preferred direction that challenges the very notion of a perfectly uniform universe. The implications are staggering. If this axis is real and not some colossal statistical fluke, it means our most fundamental assumption about the cosmos could be wrong. Perhaps the universe is not the same in all directions on the grandest scales. Maybe it has a structure, a texture, or a curvature we have not yet comprehended. Some theorists have proposed mind-bending alternatives, suggesting this alignment could be a sign that the universe is rotating, or that it is finite and shaped like a hall of mirrors, creating patterns we misinterpret. Others offer a more sobering possibility that we are seeing the imprint of something from before the Big Bang, a pre-existing architecture that set the initial conditions for our entire cosmic epoch. The scientific community remains deeply divided. Many argue the alignment is simply a trick of the light, a systematic error in how we process the data, or just an unlikely but possible random pattern in an otherwise chaotic cosmos. Yet, as new data from powerful observatories like the Planck satellite continues to be analyzed, the anomaly stubbornly persists. It is a ghost in the machine of cosmology, a subtle crack in the foundation of our understanding that hints we might not just be living in a random universe, but one with a hidden and perhaps terrifying sense of order. Our own moon holds a secret locked in ancient rock, a ghost of a force that should not exist. We think of the moon as a silent, geologically dead world, but samples brought back by the Apollo astronauts revealed a stunning truth. Billions of years ago, the moon had a magnetic field, not a weak, insignificant one, but a field that may have been as strong as Earth's is today. This presents a monumental puzzle. A global magnetic field is generated by what is called a dynamo, a churning, molten metallic core acting like a gigantic planetary generator. For a dynamo to work, it needs fuel, it needs internal heat to keep the liquid metal in motion. The problem is the moon is small. A small world cools down quickly, its internal fires snuffing out. By all our models, the moon's core should have solidified far too early to power a long-lived, powerful dynamo. So how did this small, rocky body manage to generate such a potent magnetic shield? The evidence is undeniable, etched into the very atoms of lunar rocks. As volcanic lava flowed on the young moon, tiny grains of magnetic minerals within it, like miniature compass needles, aligned themselves with the moon's global magnetic field at that moment. When the rock solidified, it froze that magnetic orientation in time. Scientists can read this fossilized magnetism, just like reading the rings of a tree, and the record shows a field that persisted for over 1 billion years. To explain this, we must reimagine the moon's fiery youth. One compelling theory involves a cosmic dance. The early moon was much closer to Earth and its orbit was different. It may have wobbled or precessed like a spinning top slowly winding down. This precessional motion could have violently sloshed the liquid in its core, stirring the molten metal with enough force to drive a dynamo, even without the intense internal heat we would normally expect. It is a delicate clockwork mechanism, one that would have eventually wound down as the moon migrated outward. Another, more dramatic theory points to a cataclysm. Perhaps a massive impact, a collision with a giant asteroid or dwarf planet, delivered a tremendous one-time shock of energy to the moon's interior. This colossal trauma could have violently jump-started the core, creating a temporary but incredibly strong magnetic field, a final brilliant flare before the dynamo faded for good. This lunar mystery forces us to reconsider what makes a world alive. A magnetic field protects a planet's atmosphere from being stripped away by solar winds, a key ingredient for life as we know it. The ghost in the moon's rocks whispers that even the quietest of worlds may have had a dynamic and potentially habitable past that we are only just beginning to uncover. Even as our own moon holds its secrets, a far greater force is pulling us through the cosmos. Our entire galaxy, along with countless others, is caught in a relentless river of motion, all flowing toward a mysterious, unseen destination. This is the Great Attractor, a gravitational anomaly of such immense power that it defies our view. It lies in the direction of the constellation Centaurus, but we cannot see it directly. Its location is hidden behind the dense, dusty plain of our own Milky Way, in a region astronomers call the zone of avoidance. Imagine trying to find the source of a mighty river's current while you are floating in its waters, blinded by a thick, permanent fog. That is our predicament. For decades, we knew something was there only by its gravitational tug. Measurements of galaxy motions revealed a colossal flow, a dark tide pulling us and our local supercluster of galaxies at a staggering 2 million miles per hour toward this single point in space. What could possess such gravity? The first clue came from mapping what we could see beyond the zone of avoidance. There, we found the Shapley supercluster, one of the most massive structures in the observable universe, a dense knot of galaxies that acts as a powerful gravitational magnet. For a time, it seemed the mystery was solved, but deeper observations revealed a troubling truth. The sheer momentum of our galactic flow is too great. The pull from Shapley, immense as it is, accounts for only a fraction of the force dragging us forward. The Great Attractor is something more. It is not a single supercluster, but likely a confluence of several, an even more enormous concentration of mass, most of it the invisible dark matter that binds the cosmos. We are being pulled toward the heart of the Laniakea supercluster, our home on the grandest scale, a vast cosmic continent of galaxies all streaming toward the same gravitational basin. The Great Attractor is not a monster in the dark, but the center of our local universe, a place where the threads of dark matter weave together to create a focal point for everything around us. Yet, even this realization does not fully explain its overwhelming influence. The true nature of what lies at that hidden center, the ultimate source of the pull, remains just out of sight, a shadow on the cosmic map that continues to draw us in. While we are pulled through the cosmos by an unseen force, another world in our own solar system displays a geometric perfection that defies the chaos of nature. At Saturn's North Pole, a storm rages, but not like any other. This is a hurricane over 20,000 miles wide, but its most stunning feature is its shape. It is a near-perfect hexagon, a six-sided figure so precise it looks engineered. This colossal polygon has been spinning for decades, perhaps centuries, a persistent puzzle etched into the clouds of a gas giant. The sides of this atmospheric giant are each longer than the diameter of Earth, and the entire structure rotates with a period that mysteriously syncs with the planet's own radio emissions. How can a fluid, turbulent atmosphere spontaneously generate such a rigid, geometric form? The answer seems to lie not in solid architecture, but in the physics of spinning fluids. Scientists have turned to the laboratory to unravel this mystery, creating miniature versions of the phenomenon. In experiments, a circular tank of fluid is placed on a rotating table, representing Saturn's spinning atmosphere. When the fluid inside is stirred at a different speed than the tank itself, something remarkable happens. Under the right conditions, stable, standing waves form, and these can manifest as polygons, with a six-sided hexagon being a particularly stable configuration. This suggests that Saturn's hexagon is a kind of planetary scale standing wave, a stable pattern born from the shear between different latitudinal bands of the jet stream. It is a natural, if breathtakingly rare, outcome of fluid dynamics on a rapidly spinning sphere. Yet the laboratory models, while compelling, are not the final word. They recreate the shape, but the devil is in the details. The incredible stability of Saturn's hexagon over such a long timescale, and its precise alignment with the planet's rotation, suggests there are factors at play we do not yet fully understand. The depth of the phenomenon is another major question. Does this hexagon extend hundreds of miles down into Saturn's liquid metallic hydrogen interior, or is it a relatively shallow atmospheric feature? The Cassini spacecraft provided us with breathtaking imagery and data, but even its detailed observations could not peer deep enough to solve the puzzle completely. The hexagon stands as a majestic reminder that the laws of physics can produce art of an unimaginable scale, a cosmic snowflake whirling in the void, whose final secrets are still locked within the churning depths of a giant. The same cosmic void that sends us fleeting radio bursts also hurled a physical object through our solar system. In October 2017, the Pan-STARRS telescope in Hawaii spotted a tiny, fast-moving point of light. It was named Oumuamua, Hawaiian for Scout, and it was the first visitor from interstellar space we had ever seen. Its trajectory was a hyperbolic arc, a path that proved it was not bound by the sun's gravity. It was just passing through, but as astronomers tracked this cosmic scout, they realized it was profoundly strange. First, there was its shape. By observing how its brightness changed dramatically as it tumbled, scientists inferred it was highly elongated, perhaps 10 times longer than it was wide, a shape unlike any known asteroid or comet in our solar system. Then came the true mystery. As Oumuamua sped away from the sun, its path could not be explained by gravity alone. It was accelerating as if pushed by an unseen force. For a normal comet, this is easily explained by outgassing. The sun's heat vaporizes ice on the comet's surface, and the jet of gas acts like a small rocket engine, giving the object a kick. But here was the problem. Oumuamua showed no visible coma, the cloud of gas and dust that always surrounds an active comet. Our most powerful telescopes saw nothing, no dust tail, no gas signature, no hint of outgassing at all. So what was pushing it? The scientific community scrambled for answers. One natural explanation proposed that Oumuamua was a chunk of solid hydrogen ice. A hydrogen iceberg would outgas without producing a visible dust cloud, explaining the acceleration and the lack of a coma. The problem is that such an object is theorized to only form in the coldest, densest cores of molecular clouds, and it is unclear if it could survive a long journey through interstellar space without evaporating. Another idea was that it was a fractal-like aggregate of dust, a cosmic dust bunny so porous and light that radiation pressure from the sun itself could have provided the push. This intense debate opened the door for a far more provocative hypothesis. Harvard astronomer Avi Loeb famously suggested we were looking at a piece of alien technology, specifically a light sail. A light sail is a thin, reflective sheet that uses the pressure of starlight for propulsion, much like a boat's sail uses wind. This, Loeb argued, would perfectly explain the object's unusual shape and its mysterious fuel-less acceleration. The sun's radiation pressure would have pushed on the thin, flat surface just as observed. The scientific pushback was swift and severe. Critics argued it was an extraordinary claim with no direct evidence and that we should exhaust all natural explanations first. They pointed out that we are only just beginning to understand the diversity of objects in our own solar system, let alone others. Oumuamua was a one-of-a-kind data point, a single enigmatic traveler that challenged our categories. Was it an exotic new type of comet, a strange asteroid, or something else entirely? It is now long gone, speeding back into the darkness, taking its secrets with it. Its brief visit left behind a single, haunting certainty that our celestial neighborhood is far stranger and more populated with unseen objects than we ever dreamed. Our solar system's edge holds a boundary as abrupt and unexplained as a cliff at the world's end. Far beyond the orbit of Neptune, in the frigid darkness, lies the Kuiper Belt, a vast disk of icy remnants left over from the solar system's birth. Astronomers expect this population of frozen worlds to continue steadily outward, gradually thinning into the Oort cloud, but that is not what we see. Instead, at a distance of about 50 astronomical units from the Sun, the Kuiper Belt simply ends. The number of objects drops off a cliff, plummeting to almost nothing. This is the Kuiper Cliff, a stark edge to our cosmic neighborhood that our models never predicted. Imagine walking along a beach where the sand simply stops, replaced by an empty ocean just a few steps out. That is the kind of jarring transition we are faced with. The most straightforward explanation for our solar system's formation suggests the Kuiper belt should extend for hundreds of astronomical units, its icy planetesimals fading slowly away. The existence of this sharp boundary implies something is actively shepherding the outer solar system, sweeping it clean or preventing objects from forming there in the first place. This has led to one of the most tantalizing hypotheses in modern astronomy, the existence of a hidden, massive planet. The gravitational influence of a world several times the mass of Earth, orbiting hundreds of astronomical units from the Sun, could be the invisible architect of this cliff. Its distant, ponderous tug would have sculpted the outer Kuiper belt, ejecting some objects entirely and shepherding the remaining ones into a sharp, confined edge. This hypothetical Planet 9 would be a ghost, felt only through its dramatic effects on the orbits of the small bodies we can see. While the evidence for this unseen world is compelling, it is not the only possibility. Another theory suggests that the Kuiper cliff is not a product of a planet, but a fossil, a frozen memory of the solar system's violent infancy. Perhaps the protoplanetary disk of gas and dust from which our planets formed itself had a sharp outer edge, maybe carved by a passing star in the Sun's birth cluster. In this scenario, the cliff is simply the original boundary of the construction site, and nothing has ever existed beyond it. Yet this, too, has its problems, as it requires a very specific and perhaps unlikely set of initial conditions. The Kuiper cliff remains one of the most concrete clues that our inventory of the solar system is profoundly incomplete. It is a silent sentinel at the frontier, pointing toward a mystery that may literally reshape our maps, waiting for a future telescope to finally glimpse the giant that cast such a long shadow. Beyond the quiet orbits of our solar system, a silent, invisible rain is constantly falling upon our world. These are cosmic rays, subatomic particles, mostly protons and atomic nuclei traveling through space at nearly the speed of light. Most are low energy, but a tiny fraction are so powerful they defy all reason. These are ultra-high energy cosmic rays, and they carry more energy in a single, minuscule particle than a major league fastball. The record holder, aptly named the Oh My God particle, detected in 1991, had the kinetic energy of a brick dropped on your toe, all packed into a single, speeding proton. Its energy was so immense it should be impossible. According to our best theories of physics, particles from distant galaxies should lose energy as they travel across the universe, bumping into the faint glow of the cosmic microwave background radiation. It is a cosmic speed limit, and these particles are breaking it spectacularly. They simply should not exist, and yet they do. The central mystery is not just their impossible energy, but where they come from. Imagine trying to find a single, specific gunman on Earth who has fired a bullet from another galaxy. That is the challenge astronomers face. When one of these cosmic cannonballs strikes the top of our atmosphere, it shatters, creating a spectacular cascade of secondary particles that spread out over miles, a sprawling air shower that our detectors can see. But by the time this shower reaches the ground, the original particle is long gone. We are left with only the scattered evidence of its destruction. Tracing its path backwards to a single point of origin is a monumental task, like finding the source of a single raindrop in a hurricane. The problem is that these particles are electrically charged, which means their paths are bent and twisted by the magnetic fields that perm the interstellar and intergalactic void. There is no straight line back to their home, so what cosmic accelerators are capable of such unbelievable feats of power? The suspects are the most violent objects in the universe. Active galactic nuclei, where supermassive black holes devour matter and spew out jets of energy, or perhaps the shock waves from colliding galaxies, which could act as a natural particle collider on an unimaginable scale. Some theories even point to gamma-ray bursts, the most energetic explosion since the Big Bang. Yet, for every candidate, there is a problem. The distances are often too great, the magnetic fields too strong, or the mechanics too inefficient to explain the sheer power we observe. The mystery is so profound that some have speculated about more exotic sources, like the decay of super-heavy dark matter particles from the early universe, or defects in the very fabric of space-time itself. Giant observatories like the Pierre Auger Observatory in Argentina are constantly watching the sky for these rare events, mapping the arrival directions of millions of cosmic rays in the hope of finding a pattern, a slight overdensity in the cosmic static that points to a source. So far, the results are tantalizing but inconclusive, hinting at possible origins in broad areas of the sky rather than at specific, identifiable objects. Each ultra-high-energy cosmic ray is a messenger from the most extreme environments in the cosmos, carrying a coded message about its violent birth. The problem is, we have not yet learned how to read the address. The silent rain of cosmic rays is a testament to the universe's raw power, but some of its most beautiful creations are born from a far more gentle, yet equally mysterious process. Drifting in the constellation Monoceros, a celestial artist has crafted a masterpiece of perfect geometry. Known as the Red Rectangle Nebula, this structure is anything but the chaotic, bubble-like cloud you might expect. Through the lens of the Hubble Space Telescope, it reveals itself as a stunning, intricate ladder of glowing rungs, all contained within a near-perfect X-shape. At its heart lies a dying star, HD 44179, which is in the final stages of shedding its outer layers. Most stars in this phase create beautiful, spherical planetary nebulas like delicate glass ornaments blown into space. The red rectangle defies this convention completely. Its sharp, angular form looks engineered, as if a cosmic architect drew it with a straight edge. So what force corrals the outflowing gas and dust into such rigid, linear structures? The secret appears to lie in a dense, dusty disk that tightly encircles the central star. Imagine a giant, flat donut of dust spinning around the star, so thick that it blocks material from escaping along the star's equator. When the star ejects its outer layers, this dense disk funnels the material, forcing it to shoot outward only from the star's poles. This creates two opposing jets or a bipolar outflow. But that alone would create an hourglass shape, not a rectangle with rungs. The final, crucial ingredient is a wobble. The star, or its disk, is thought to be precessing, meaning its axis of rotation is slowly wobbling like a spinning top winding down. As the star fires its polar jets, this wobble causes the streams of gas to trace out a conical path through space. From our vantage point, looking almost directly at the side of this cone, the edges appear as the long sides of the rectangle, while the concentric waves of earlier ejections form the glowing rungs. It is a natural lighthouse in the void, its beam slowly sweeping across the cosmos. Yet, even this elegant explanation leaves questions unanswered. The precise composition of the dust in the disk, which gives the nebula its deep red color from a type of organic molecule, is still not fully understood. The stability of this precise configuration over thousands of years remains a subject of intense study. The Red Rectangle Nebula stands as a breathtaking example of how simple physical laws, when combined in just the right way, can produce art of an almost mathematical purity, a cosmic emblem whose final secrets are still locked within the dance of a dying star and its dark, confining disk. Deep within the heart of our own galaxy, a brilliant and mysterious glow defies easy explanation. The center of the Milky Way should be a familiar place, home to a supermassive black hole and a dense cluster of ancient stars. Yet when the Fermi Gamma Ray Space Telescope began scanning the sky, it revealed something startling, an intense and diffuse excess of gamma-ray radiation blossoming from the galactic core. This is not the sharp, pinpoint light of individual stars, but a vast, foggy luminescence that permeates the central region, stretching thousands of light-years across. It is as if the galaxy's engine room is leaking a powerful, invisible energy, and we are only just now seeing the spill. The discovery of this galactic center excess sent a wave of excitement through the astrophysics community. primarily because one of the leading explanations points directly to the universe's greatest unknown, dark matter. The theory is as elegant as it is profound. If dark matter is indeed made of WIMP, those hypothetical weakly interacting massive particles, then they should be concentrated most densely in the galactic center, drawn in by the immense gravity there. And wherever dark matter particles are densely packed, they might occasionally collide with one another. According to some models, when a particle of dark matter meets its antimatter counterpart, they would annihilate each other in a flash of pure energy, converting their mass into a cascade of secondary particles, including the very gamma rays that Fermi sees. This glow could be the first indirect evidence of dark matter, the ghostly signature of its self-destruction at the core of our home galaxy. But the universe is rarely so straightforward. A compelling alternative has emerged, one that involves not exotic new physics, but a chorus of faint, spinning stellar corpses. The galactic center is a crowded, tumultuous place, and it could be teeming with thousands of pulsars, the ultra-dense, rapidly rotating remnants of massive stars. These cosmic lighthouses beam out powerful jets of radiation, including gamma rays, as they spin. Individually, these pulsars would be too faint and too close together for Fermi to resolve as distinct points of light. But collectively, their combined, smeared-out emission could perfectly mimic the smooth, extended glow of the gamma-ray excess. It is the difference between hearing a single violin and a massive orchestra, the individual instruments blurring into a single, powerful sound. So how do we tell the difference between the symphony of pulsars and the whisper of annihilating dark matter? The search is on for the telltale clues that would crack the case. If pulsars are the source, then more sensitive radio telescopes should eventually be able to pick out individual point sources from the haze, turning the fog into a collection of distinct stars. The hunt for these faint pulsars is ongoing, a painstaking effort to find the needles in the galactic haystack. On the other hand, if the signal is from dark matter, its glow should be perfectly smooth, and it might also appear in other places where dark matter is thought to cluster, like dwarf galaxies orbiting the Milky Way. The data from these dwarf satellites is still inconclusive, adding to the suspense. This is the heart of the scientific debate, a classic battle between the known and the unknown. Are we seeing the collective breath of a vast population of familiar, though elusive, stellar objects, or are we witnessing the first faint smolder of the universe's most dominant, yet invisible, component finally revealing itself? The answer remains suspended in that brilliant, enigmatic glow, a cosmic question mark written in light at the center of everything we know. The rules that bind the atomic nucleus are strict and absolute. Protons and neutrons cling together in a delicate balance, held by the strong nuclear force, and conventional physics insists that you cannot have a cluster of just neutrons on their own. A nucleus with only 2 neutrons is unstable, and a 3-neutron system is thought to be impossible. Yet, in a series of fleeting experiments, physicists may have witnessed the impossible, a tetraneutron, a ghostly nucleus composed of 4 neutrons and nothing else. The first tantalizing hint emerged in 2001 from a particle accelerator experiment in France. Researchers were firing beryllium nuclei into a carbon target, a process that can knock fragments loose. In the resulting debris, they detected signals consistent with 4 neutrons arriving at their detectors simultaneously. The statistics were weak, a mere glimpse that many in the scientific community dismissed as a probable fluke, perhaps 2 pairs of neutrons that just happened to strike at the same time. The case grew far stronger in 2016 when a Japanese team employed a more precise method. They fired a beam of helium-8, a rare and unstable isotope, at a target of liquid helium. The collision was designed to be clean. The helium-8 nucleus, containing 2 protons and 6 neutrons, would strike a regular helium-4 nucleus with 2 protons and 2 neutrons. The result was staggering. The collision seemed to knock out the 4 neutrons from the helium-8, leaving the 4 neutrons from the target helium nucleus momentarily bound together before they flew apart. The data indicated a resonant state, a temporary, unbound particle that lived for just 1 × 10⁻22 seconds. That is a billionth of a second, but in the quantum world, it is long enough to be a real, identifiable entity. If confirmed, the implications would shatter a cornerstone of nuclear physics. The Pauli exclusion principle, which governs the behavior of particles like neutrons, makes it incredibly difficult for identical particles to occupy the same space unless they have different quantum states. Forcing 4 neutrons into such a tiny, temporary bond should be like trying to push the same poles of 4 powerful magnets together. They should violently repel. The existence of a tetraneutron suggests there is a new, unknown force or a new kind of nuclear interaction at play, one that can, for the briefest of moments, overcome this fundamental repulsion. It hints that our understanding of the strong force is incomplete, and that exotic states of matter, perhaps even stable islands of pure neutron material, could exist in the crushing densities of neutron stars. For now, the tetraneutron remains a controversial specter, a quantum phantom whose very existence challenges us to rewrite the rules of reality. The orderly spin of planets can be shattered by a single, violent encounter. Uranus stands apart from every other world in our solar system, not for its color or composition, but for its orientation. It is a planet that has been knocked on its side. Its rotational axis is tilted a staggering 98 degrees, meaning it essentially orbits the Sun while rolling along its equator. Imagine a bowling ball set spinning with its pole pointing directly at the ground. That is Uranus, a world with seasons of absolute extremes. For a quarter of its 84-year orbit, one pole is bathed in continuous sunlight, while the other is locked in a frigid, decades-long night. Then the roles reverse. This bizarre configuration is almost certainly the scar of a primordial cataclysm. The leading theory is that in the chaotic early days of our solar system, a young Uranus was struck by a protoplanet at least twice the mass of Earth. This was not a glancing blow, but a direct, shattering impact that literally tipped the entire world over. The collision would have been unimaginably violent, likely vaporizing a significant portion of the planet's icy mantle and scattering debris everywhere. Some of that debris may have coalesced to form Uranus's system of rings and moons, which themselves orbit in the same tilted plane as the planet's equator, a fossilized record of that ancient impact disk. Yet, for all the elegance of this theory, profound questions remain. The physics of such a collision are incredibly complex. How did the impactor deliver its momentum so perfectly to tip the planet without completely shattering it? Why does Uranus's magnetic field, which should be generated deep within its core, also appear tilted and wildly off-center? Some simulations suggest the cataclysm might have happened while Uranus was still surrounded by its own protoplanetary disk, with the surrounding gas and dust helping to dampen the chaos and shape the resulting system. Others propose it was not one single impact, but a series of smaller, successive collisions that gradually pushed the planet over. The precise timing is also a mystery, as such an event could have radically altered the planet's interior, perhaps explaining why Uranus seems anomalously cold compared to its sibling Neptune. The planet's extreme tilt is more than just a curiosity. It is a frozen moment of cosmic violence, a clue to the brutal formation of our solar system that we are still learning how to read. The universe's first 3 minutes should have left a very specific chemical signature. In that initial, searing burst of nucleosynthesis following the Big Bang, space was a frantic nuclear furnace, fusing the primordial soup of protons and neutrons into the first light elements. The models are exquisitely precise, predicting how much hydrogen, how much helium, and crucially, how much of a specific isotope, lithium-7, should have been forged. And for the most part, the predictions match spectacularly with what we observe in the oldest, most pristine stars. But for lithium, the numbers are catastrophically wrong. The oldest stars contain only about 1/3 of the lithium that our best theories insist should be there. This is not a small rounding error. It is a fundamental discrepancy that has persisted for decades, a glaring mismatch between our grand cosmic recipe and the actual ingredients found in the fossil stars of the early cosmos. Where did all the lithium go? One possibility is that our understanding of stellar interiors is fundamentally flawed. These ancient stars are like cosmic time capsules, their outer layers preserving the chemical composition of the early universe. But what if these stars are not perfectly pristine? What if, over billions of years, they have been slowly destroying the very lithium we are trying to measure? Deep within a star, turbulent currents could drag surface lithium down into the hotter interior, where temperatures are high enough to burn and destroy it. This process, known as diffusion or microscopic settling, could gradually deplete the surface layers of lithium, hiding the true primordial abundance from our telescopes. The problem is that our models of stellar physics struggle to account for the precise and consistent factor of 3 depletion we see across so many different stars. Another, more profound possibility is that our models of the Big Bang itself are incomplete. Perhaps there is a piece of nuclear physics we are missing, an unknown reaction pathway that consumed lithium in the universe's first few minutes. Or maybe there is an entirely new type of particle, like a certain type of dark matter, that interacted with the primordial plasma and altered the nuclear chain reaction, effectively erasing lithium before the first stars ever formed. This lithium problem is a quiet but persistent thorn in the side of cosmology. It tells us that for all the majesty of the Big Bang theory, a crucial page is missing from the story of our cosmic origins, a lost chapter written in an element we are only just beginning to understand. Some cosmic structures look so perfectly formed they seem to defy the chaos of their own creation. Hoag's object is one such marvel, a galaxy that appears as a cosmic bullseye floating in the void. At its heart lies a dense, spherical core of ancient yellow stars, glowing with the warm light of stellar old age. This core is encircled by a perfect, detached ring of vibrant blue stars, younger and hotter, separated from the central core by a gap of near-total darkness. It looks less like a naturally occurring galaxy and more like a piece of celestial jewelry, a ring tossed perfectly around a central jewel. The symmetry is so flawless it feels intentional, yet it presents a profound puzzle for astronomers. How does such a perfect structure form and maintain its pristine shape? The most intuitive explanation points to a violent past, a galactic collision. The theory suggests that billions of years ago, a smaller galaxy might have plunged straight through the heart of what is now Hoag's core. This cosmic cannonball shot would have sent ripples of dense gas and dust propagating outward, triggering a wave of new star formation in a perfect circle, much like a stone dropped in a pond creates circular waves. The problem is, there is no sign of a perpetrator, no mangled galaxy remnant or stellar debris that would be the expected aftermath of such a dramatic event. The entire system is clean, serene, and perfectly balanced. The other leading theory is one of extreme resonance, a delicate gravitational dance. In this scenario, a central bar of stars, a common feature in many galaxies, could have once existed in Hoag's object. Over time, the gravitational forces from this rotating bar would have funneled gas and dust into specific, stable orbits at a precise distance from the core, a resonance ring where star formation was ignited. Once the bar itself dissolved, it would have left behind the perfect ring we see today. But this process is incredibly delicate, and the ring's almost mathematical perfection pushes the limits of this explanation. Hoag's object stands alone, a singular example of such symmetry. Its very existence challenges our understanding of galactic evolution, forcing us to wonder if we are witnessing a rare, fleeting moment of cosmic order, or if the universe holds secrets of structure formation we have not yet begun to grasp. Even the most precisely calculated cosmic journeys can be thrown off by a phantom push. When spacecraft like Galileo or Rosetta swung past Earth to steal a little gravitational energy for their long voyages, ground controllers noticed something strange. Their velocity, tracked with absolute precision, would show a tiny, unexpected increase, a minuscule but undeniable kick that our best models of orbital mechanics failed to predict. This is the flyby anomaly, a ghost in the machine of interplanetary navigation. The effect is incredibly small, often just a few millimeters per second, a change so subtle it would be negligible on a car trip. But for a probe traveling millions of miles, that tiny error compounds, revealing a gap in our understanding of the forces at play right here in our own celestial backyard. The inconsistency is what makes it so baffling. It does not happen on every flyby, and the magnitude of the boost seems to vary in ways we cannot yet explain. So what is giving these spacecraft an unaccounted-for push? The most straightforward explanations point to earthly imperfections. Perhaps it is unmodeled atmospheric drag, or the subtle pressure of solar radiation, or even tiny errors in how we account for Earth's uneven gravity field. Yet when scientists meticulously recalculate these factors, the numbers still do not quite add up. This has led to more exotic and controversial possibilities. Could it be evidence of dark matter exerting a faint, localized drag in our planet's vicinity? Or does it point toward a need to modify our theory of gravity itself, suggesting that Einstein's equations require a tiny adjustment for specific orbital geometries? The phantom push remains an unsolved puzzle, a whisper from the void that even our most trusted maps of space and time contain uncharted corners. These vast cosmic deserts are not merely empty space between the glittering cities of galaxies. They are voids, incomprehensibly large regions of nothingness that stretch for hundreds of millions of light years, containing almost no galaxies, no stars, and very little matter. The Boötes void is one of the most famous, a spherical chasm so enormous that our entire local group of galaxies would be a mere speck within its staggering emptiness. If the Milky Way were at its center, we would not have known other galaxies existed until the 1960s. The existence of these voids is a direct prediction of our understanding of the cosmos, sculpted by the gentle pull of dark matter and the push of dark energy over billions of years. Dense regions grow denser and empty regions grow emptier in a process known as gravitational evolution. Yet the sheer scale of the largest voids is straining that very explanation. They are so immense and so profoundly empty that some cosmologists wonder if they are simply too big to have formed in the time available since the Big Bang. Could these voids be more than just statistical flukes, the natural outcome of random chance in an unimaginably large universe? Or are they telling us that the initial seeds of the cosmos imprinted in the Big Bang had a stranger pattern than we thought? Perhaps an unknown force, a type of cosmic repulsion associated with dark energy, actively helped to carve out these empty regions, pushing matter away and creating these staggering bubbles of nothing. The voids stand as silent, hollow monuments to a mystery on the grandest of scales, challenging us to explain not just the universe's bright structures, but its profound and deliberate emptiness. A ghostly pyramid of light sometimes rises from the horizon just after sunset or before dawn. This ethereal glow, known as the zodiacal light, has been a celestial fixture for as long as humanity has watched the skies. It appears as a faint, tilted pillar stretching upward, following the same path across the heavens as the sun and moon. For centuries, we understood its source, sunlight gently scattering off a vast cloud of fine dust grains that fills the inner solar system. This dust is the leftover grit from asteroids that smashed together and the crumbling tails of comets that passed too close to the sun. It forms a colossal, lens-shaped cloud centered on our star, and its gentle radiance was considered a settled, beautiful fact. But recent, precise measurements have shattered that calm understanding, revealing a startling deficit. When scientists finally tallied the total mass of this interplanetary dust cloud, the numbers did not add up. The cloud is far too light. Based on the rate of dust production from all the known asteroids and comets in our solar system, there should be roughly 400 million tons of this fine material drifting between the planets. The actual measured mass is a mere fraction of that. A colossal amount of dust is simply missing. This is not a small accounting error, it is a void at the heart of our cosmic neighborhood. So where did it all go? The leading suspect is a subtle but relentless process called the Poynting-Robertson effect. As a tiny dust grain orbits the sun, it absorbs sunlight from the front and re-radiates that energy as heat in all directions. This act of re-radiation creates a tiny but constant drag force like a perpetual headwind. This drag slowly bleeds energy from the grain's orbit, causing it to spiral inexorably inward toward the sun, where it is eventually vaporized. It is a cosmic conveyor belt, constantly feeding the inner solar system's dust into the sun's fiery embrace. The problem is that this slow spiral takes thousands of years, and the math suggests the current inflow rate cannot account for the dramatic shortage. The dust we see falling in is not enough to explain the dust we do not see out there. This forces a dramatic rethinking of our solar system's recent history. Perhaps our cosmic backyard was not always this tidy. The most compelling explanation is that we are living in the aftermath of a recent and exceptionally massive cosmic collision. Imagine a single catastrophic event, like the destruction of a large asteroid or a dwarf planet, occurring just within the last million years. Such an impact would have ejected a stupendous amount of fresh dust into the inner solar system all at once, creating a temporary, brilliant zodiacal cloud far denser than the one we see today. We are now witnessing the fading echo of that event as the Poynting-Robertson effect efficiently cleans up the debris. The current dust cloud is not in a steady state, but is instead a temporary and rapidly vanishing remnant. The faint glow of the zodiacal light is no longer just a peaceful curtain of light, but a clock ticking down the time since a forgotten cataclysm. Its dimness is not a sign of calm, but a measure of a violence so recent that the dust has not yet finished settling. Our most precise measurements of the cosmos are now in open conflict. The universe's expansion rate, a number we call the Hubble constant, is at the heart of modern cosmology. It tells us how fast galaxies are receding from us for every million parsecs of distance, a fundamental speed limit for the entire cosmos. We have two primary and supposedly reliable ways to measure this number. The first method looks at the local modern universe. Astronomers use stellar lighthouses like Cepheid variable stars and Type 1, a supernova, to gauge distances to nearby galaxies. By comparing these distances to the galaxy's redshifts, they can calculate a current local value for the Hubble constant. The other method peers back to the dawn of time, using the cosmic microwave background, the ancient afterglow of the Big Bang. By meticulously mapping the subtle temperature fluctuations in this primordial light, we can infer the universe's initial conditions and, running the cosmic film forward using our best models of physics, predict what the expansion rate should be today. These two methods should arrive at the exact same number. They do not. The local measurement gives a faster, more frantic expansion rate. The early universe measurement predicts a slower, more sedate pace. This discrepancy is not a small, negligible error bar overlap. It is a stubborn, growing chasm that has persisted despite years of increasingly precise observations and frantic reanalysis. This is the Hubble tension, and it is shaking the foundations of cosmology. It suggests that something is fundamentally wrong, either with our measurements or, more thrillingly, with our model of the universe itself. Perhaps dark energy is not a constant but an evolving force that has grown stronger over time. Or maybe there exists a new, previously unknown type of subatomic particle that flooded the early cosmos, altering its expansion history. Some theorists are even forced to consider that our understanding of gravity itself is incomplete on the largest scales. The Hubble tension is more than a statistical anomaly. It is a direct challenge, a cosmic clue that our most successful story of the universe is missing a crucial and perhaps revolutionary chapter. From the ghostly tug on our spacecraft to the silent, hollow voids between galaxies, these 25 cosmic puzzles span every conceivable scale of reality. They reach from the quantum realm of a fleeting tetraneutron to the unimaginable expanse of dark energy pushing the entire cosmos apart. Each one is a testament to the limits of our current knowledge, a frontier where our most brilliant theories meet phenomena they cannot explain. They are not failures of science, but its very engine, the unanswered questions that drive us to build better telescopes, dream up new physics, and peer ever deeper into the darkness. The universe is not a puzzle to be solved, but a mystery to be explored, and it is far stranger, more violent, and more beautifully intricate than we ever could have imagined. So we turn the question to you, of all these cosmic riddles, which one captures your imagination the most? Is it the silent promise of dark matter, the impossible speed of the universe's expansion, or the brief, brilliant flash of a signal from the void? Let us know in the comments, and never stop looking up with wonder.